Hello, Black Hat. Thank you for coming to this session. In today's talk, we are going to deep dive into a way to search for RPC functions to coerce authentication in Microsoft protocols. So my name is Remi Gascou. I'm also known as Podalirius in the information security scene, and I'm a security researcher and speaker in France, where I do mostly pen tests and vulnerability research. My principal research subjects are Windows Active Directory security and recently mainframes. In this 30-minute session, we are going to go through a background on what is RPC and why we are going to need it, what are Windows coerced authentications, even though they are still not patched in all of the functions in Windows, we are still needing them in offensive security. What is the state of research up to this point to coerced authentications that are using RPC functions, and we'll see how we can parse the Microsoft Open Specification documentation to extract and create new functions to parse the IDL and auto-generate proof of concept code that we'll use to find new coerced authentications. After that, I'll present Coercer, which is an all-in-one tool to coerce authentications for your pen tests. And finally, I'll leave you with defense techniques and 3 takeaways from this talk. So when we are inside an Active Directory domain, we have many Windows machines that communicate with each other using various network protocols. One of them is called the remote procedure call, or in short, RPC. And basically, it allows to call a remote function on a remote machine. For example, we can, from a user PC, ask for something on the DC to work. And it's called a remote procedure call, to call a remote function on a remote machine. Of course, you can call this function with parameters, and you will get a return value or a return structure. In case of a file descriptor, for example, you can have a print handle or a file descriptor in response. To call a remote procedure, we need 3 things. Firstly, we need to know in which RPC interface this function is defined. An RPC interface is defined by a couple of universally unique identifier and a version. And we'll need to know what is the operation number of the function. The operation number of the function uniquely defines this function inside the interface, because inside an interface you will have many functions, and they are all listed inside kind of a list, and the operation number is auto-incremented to define each function. And finally, we'll need the parameters, just as any function in any programming language. So if we take an example of a simple RPC to understand what is a coerced authentication, imagine a function called RPC copy file that you can call remotely on a machine, allowing to copy a file from a source to a destination file. You cannot call it anonymously, because anonymous calls can be a vulnerability per se. We will assume that you can just call it with a normal user in the domain. So when we are calling these functions, it can be even pretty useful when you are doing administration of remote servers, because you can copy backup files and you can do stuff like this. But it can be leveraged by an attacker because it manipulates file paths. We'll see that this harmless call can be used. For example, if we use it on a local file, it's simple. Everybody here knows what it will happen. You call the remote procedure, the file is copied, and you'll get a return value in return, and you perform a local file copy. But what if we changed inside the source file the path to a local file by a UNC path on Windows, targeting a remote server, in this case RServ1, to find a file that is hosted on a remote share? What will happen then is that when we will call this remote procedure on DC01, DC01 will try to copy this file from the source file. But this source file does not exist. The source file is hosted on another server. So DC01 will try to access over SMB to SRV01. SRV01 will return the file content, and the file content will be stored on DC01. Finally, we'll have our return value or our return structure. In this case, it's a legitimate example, so it's not a problem as per se. But we'll see that as an attacker, we can perform the same operation, but ask DC01 to retrieve a file that is hosted on one of our SMB servers. It can be on the same machine or on another machine. In this case, it's all on the same machine. So we perform an RPC call to ask for DC01 to retrieve a file that is hosted on our server. What happens then is that in the step 2, DC01 will try to authenticate to our machine to access the SMB server. Firstly, it will need to try to authenticate using the null session to access it anonymously. And if we respond by saying that you cannot connect anonymously to this SMB server, then it will try to authenticate using its current session. And in this case, if the program running the RPC server runs as anti-authority system, you will be authenticated as the CO1 dollar, the machine account of the machine. And we can return whatever error code we want as access denied, invalid credentials, or whatever things you need, because we do not need to actually give the file content to DC01. And finally, we'll get a return value. But in the meantime, we got the actual hash of an authentication from DC01. And depending on whether this hash is an NTLMV1, NTLMV2, with or without SSP, you can do lots of things with it. It's not an attack per se at this moment, but with this first step, you can perform many attacks afterwards. If it's NTLMV1, NTLMV2, with or without SSP, you can either relay this hash to connect elsewhere, or you can crack it locally to retrieve the MD4 password, the NT hash, of the machine account or the account that authenticated. These kind of attacks are not new. In fact, the first one, which was widely known at the time, was the PrinterBug, which was found in 2017. And after that, with PetitPotam in 2021, we saw around 4 new attacks in 4 different protocols in less than a year. So we can only wonder what's next, what will be the next goal, because if we can find 4 new ways to coerce authentication through RPC in 1 year, it surely means that there's many others. And as there are thousands of RPCs out there, it's quite probable that we find new ways. So I was wondering, what can we do to automate the search of RPC functions? Because up until this day, when coerced authentication through RPC was found, it was found by reading semi-manually the Microsoft OpenSpecification docs with PDFs or online, and try to understand how the RPCs works, and what function can be interesting to coerce authentication. So there are 2 ways to find new vectors to coerce authentications. The first one is to reverse executables and programs that are on the machine which have RPC servers in them. But the main drawback of this approach is that you have to have all the services installed on the machine, and you cannot do that automatically. You cannot install all of the Windows services on one machine, because the machine will start to bug if you actually install everything that you want on a DC. And sometimes, even if the service is installed, it does not mean that the remote version of this service is activated. So sometimes the service is working locally, but you cannot call it from another machine. So this way is really accurate, but it's really complicated to do. And the other way is way more as a wide attack surface, because we can see every function of every protocol by parsing the Microsoft OpenSpecification documentation. But we cannot test it because we will need also to have the services installed on the machine. So we'll have to, by hand, install the services. But we'll find way more functions by parsing the docs. So when I chose to parse the Microsoft OpenSpecification docs, I had 3 main objectives in mind. The first one is to find all the RPC protocols with their IDL files if present. IDL stands for Interface Definition Language. I wanted to find all the interfaces, the RPC interfaces, with all the functions that we'll need to use, and how to access them, and list all the arguments of all the functions so we can see what they are, if they are interesting, and their operation number. Microsoft OpenSpecification docs looks like this. You have a page inside MS Docs where you have every RPC protocol described protocol by protocol. And when you click on this protocol, you will have all the documentation that you find in the PDF in online version. And on the left, you see multiple sections. These big sections are introduction, messages, security examples, protocol examples. You will have a lot of things, and inside it, you have various sections that can be very useful to find information for this research. The first one is the section 2.1 transport, which in most of the case, will hold all the information we need to connect to the service that runs these RPCs. Sometimes it's not complete because all the pages of the Microsoft Docs are not equal, and sometimes you won't have the UID and the version of the RPC interface. So if the information is here, it will be in this page, but sometimes it's not. The major problem of this page is that it's written in natural language, so it's quite complicated to parse, even though we can use regular expression to extract the UID of the RPC interface. To find the versions, it's quite complicated, and sometimes they are not inside these pages. So one of the ways to find all this information is to parse section 6 of the documentation, which contains a full IDL. It does not always contain the interface definition language, because sometimes the IDL is not public. But when it is public, we have a file containing all the interface definition language, which defines the interface, the functions that are in it, and a lot of arguments and type structures and types that are used in it. And as you can see here, on the top of the file, you have the UID and version of the RPC interface that is listening. And they are always here because it's the interface definition language that is used by developers to develop the interfaces. So if we have this file, we also have the UID and the version. If we scroll down a little bit, we also have all the prototypes of all the functions that is used in this interface. Although we do not have the source code, we have the prototypes, but we only need it to know how it works and if it manipulates file paths. So as you can see, we have functions, we have the types, the return types, we have properties of each argument, and we have argument names, but we do not have the operation number. Simple. The operation number is basically auto-incremented in this file, so we just have to parse this file, and we'll know everything we need to connect to these remote functions. If we look more closely at what a function looks like, we have a return type, a name, properties, type name for each argument, and argument names. Argument names are really useful in RPCs because they are almost never obfuscated, which means they typically describe what they are doing. So server name is basically a server or an IP address. Root share is an SMB share. Comment, it can be a comment of a new share that you will create, of a new DFS namespace. And through these arguments, we can actually know we can know if they are going to manipulate file paths, and therefore if they are going to accept UNC paths to force the machine to authenticate on SMB server. What we can do is we can analyze all the RPC functions known to Coerce authentications up to this day, and we see that every function known up to this day to Coerce authentications is using either path, share, file name, printer name, server name inside one of these arguments as the attack vector. And the UNC path is always injected in one of these arguments. So if we try to create a model to look for all of the functions that use these arguments to Coerce authentications, we can start from this and just parse everything in the documentation and list every function that has these names inside its arguments. So what we are going to do is we are going to parse the Microsoft Open Specification documentation page where every RPC protocol is listed. For each RPC protocol, we are going to list every section and see if section 6 is existing. If section 6 is existing, we are going to extract and parse the interface definition language of this function and of this interface and its functions. And for each function, we are going to extract all the functions with their parameters and get the RPC interface UID and version that will be defined inside the IDL file. Now that we're here, if we implement a model using the names that we saw just before, we can extract all the functions that have names that are lookalike with file name, server name, printer name, share, or sometimes UNC path. Some of the functions have UNC path in their names. And we can extract almost 250 calls. And inside them, we can easily find back known calls with PetitPotam in the encrypting file system protocol, EFS. We find back cheeseounds on event log. We find DFSCoerce on dynamic distributed file system namespace protocol. We find PrinterBug, and we find every existing Coerce authentication through this. But now that we have a list of functions that are promising, what we want is to automate most of the work to create proof of concept, because it's one of the bargains of this research was to find the actual functions that we are going to use, but the other part is to automatically generate proof of concept, because we are not going to write a 200 proof of concept by hand. Firstly, what we need to do is to write a program in Python using Impacket. It's a library used to connect to Windows machines for offensive attacks in Python. And we are going to write a simple file in Python to coerce authentication using one of the actually known coerced methods. We can use PetitPotam or whatever call you want. We write a Python code, and then we are going to try to automate it to change everything that is specific to the call that we use, such as the RPC interface, the name of the call, the arguments of the functions, to create a Python template using Jinj2. And it will look kind of like this. So it's really not Python code anymore, and it's absolutely ugly, but it will allow us to generate proof of concept code for each of these calls. What you see here is when you are going to connect to an RPC server using Impacket, you need to use two structures, one for the RPC call and one for the RPC response, to parse and to create structures. And this template allows to create the structures so that we can perform the RPC call and parse the response. What it looks like once it's generated, it's way beautiful. And as you can see, there is the operation number that we saw in the last slides, and the structure, which contains all of the names of the arguments, as well as the Impacket types that you see inside the brackets. And afterwards, in the comments, you see what was the type that was actually written inside the ideal files, because the Impacket type and the ideal type are not the same. So I kept these types in comments, because if we need to debug, at least we have it. And as you can see in the response, I left an empty structure because we actually don't need to parse the response. So I decided to just create an empty structure, which Impacket will try to parse, but as it's an empty structure, it will not parse the actual response from the SRB server. We can parse it if we want. We can implement it to have the actual response that was returned by this call, but most of the time we don't need it, so we won't bother doing it. This is the next part of the Jinj2 template, which is even uglier, because Jinj2 mixed with Python is not pretty, honestly. But we are going to create a class which basically does everything that we need. We are going to create a class that takes the UID, the version, the RPC function name, and its arguments. And this class is going to trigger this call and just trigger it. We won't parse the response. We will have a response, but Impacket will pass nothing because we have an empty structure. So this is the Jinj2 template. You can watch it more carefully in the slides afterwards, because it's not really pretty to project. And once it's generated, it's beautiful Python code. And you have a class with the name of the protocol. This one is DFSCoerce. It was found in June, I think. And you have the UID, the version, SMB pipe to connect to. And then you have a function, which is called the same as the RPC function that we are going to call, to coerce the authentication through the server name variable. As you can see, the server name variable actually takes an IP, a NetBIOS name, or a domain name, followed by a null byte. And we have root share, comment, and whatever thing you want. And we just put random data, random names, random ASCII strings to populate them. And as you can see, in the last lines of the codes, we see self-dcu.request. It's the actual line that tells Impacket to perform the DCU RPC request to the remote machine. As I said before, we have a problem with ideal types and Impacket types because they are not consistent, and Impacket uses Python structures to create these types because they are not really existing in Python. So we need to keep in mind that we are going to need to create a translation table between the two. because IDL and Impacket types are not the same, and sometimes three IDL types will be translated to the same Impacket type. As we can see here, the white char T, white char, and white char pointers are always translated into white string in Impacket. The main limit of this method is that, as I said before, we don't necessarily know how to enable the services, because this part of the Microsoft documentation only focuses on the developer side of these RPCs. Therefore, we need to know how to enable the services, and sometimes it's not written inside the docs. And also, some protocols do not have their public IDL code. As they do not have their public IDL code, there is something we can do which allows us to still parse a bit of these functions. Is in the section headers of the documentation, you have the name of the functions followed by parentheses, openum, and the operation number. So therefore, if we do not have the IDL code, we could parse section by section for all the functions of the protocols and extract the HTML or the markdown source of the documentation to understand what is the parameters of the function. So following this research, I published every proof of concept with their README files and everything of this research in open source. So if you want to check it, it's on GitHub. And it's still being 3H because, as I said before, we have to activate each of those services, and sometimes it's not really clear, or we cannot activate them anymore. It's only on Windows Server 2008, for example. So it's quite complicated to 3H by hand, but at least we have all the readmes with all the information, RPC interfaces, UIDs, and Python proof of concept code using Impacket that is inside this repository. There is one folder per protocol, and in each of these folders you have one folder per function containing the proof of concept code and the README file. The README files contains all of the documentation, all of the links to the actual documentation, so you can find where the information comes from. And you will have the operation number, the RPC interface with how you can access them. For example, the list of SMB pipes that is used to access them. And if you want to access it on GitHub, there is QR code here, so feel free to scan it. And finally, inside this repository, you also have a README file for each of these calls with a short description of basically what is a coerced authentication, but specify for this call. Meaning, if we are using the encrypting file system, it's really easy because we perform one call using file name and UNC path, and we have already a coerced authentication. But in the case of PrinterBug, for example, PrinterBug uses the printer handles, so you need to open a printer, retrieve the handle, so parse the actual RPC response, and then use this handle to coerce an authentication. So in this case, it's really useful to have a description piece by piece of what is happening to coerce this authentication. For the pen testers and researchers that are doing coerced authentications inside their pen tests, I wrote something called Coercer, which takes all this research and applies it to pen tests really easily. Basically, I use everything that is actually known as RPC calls, and next RPC calls will be added once we find some in the slides. And there is three modes. The first one is the scan mode that is intended for defense purposes. In scan mode, you just have to give a user of the domain, and it will try to authenticate to every RPC function through every interface and through every SMB pipe on the remote machine. And as you can see, we already know inside this tool if we got an SMB authentication directly inside the tool. We do not need to have other tools such as NTLM relay or responder to use it. And this one is more intended to scan for a remote machine, for example, to see if your net filter rules to prevent RPC calls from another machine worked. The second mode is the Coerce mode, which is widely used in pen tests. When you are doing coerced authentication, you can coerce through every possible call through this mode. You can either use it with authentication, with a user authentication, or without authentication. In case you use an authentication, it will try to authenticate through every SMB pipe in which this call is known to work. And you will have the SMB authentication that will go to another server. There is no SMB server in the Coerce mode of Coercer, so you can use a responder or NTLM relay to actually perform the attacks. And finally, there is a fuzz mode for the research folks. If you want to fuzz every call, every payload through every SMB pipe on lots of machines, you can perform it on many machines. It's basically like burp intruder, but for RPC calls using various payloads on RPC calls. And you will have, as you see, the error codes and the SMB authentications is actually what we receive from the RPC response. So if you see an error code, it's the error code that we received from the authentications, and the SMB authentication is that we actually received an SMB request from the remote machine. So to wrap up this talk, I want to remind a few defense techniques because coerced authentications are not a vulnerability per se. They are just a way of how Windows works, and they will not be patched. So we need to prevent them from happening by adding external security to this. So when we have a coerced authentication, basically the machine that is attacked will connect back to the attacker using outbound SMB and or TCP/IP or whatever connection you want. And when we have this kind of connections, we can prevent them through three vectors. So first one is to disable all the unused services. It seems rather logical, but you'd be surprised on how many domain controllers you see out there with the principal still activated up to this day in 2022. But we need to disable all the unused services and more importantly, to disable all the services and enable only the ones that we need. Secondly, we need to enable the extended protection for authentication. This one is really important, but it will not prevent the coerced authentication. It will only prevent the relay of credentials once the coerced authentication has taken place. So an attacker will still be able to receive the authentication, but it will only be able to crack it locally. It will not be able to relay it on the network to authenticate elsewhere. And finally, if you can put on network sharing on your network infrastructure and rules to prevent unauthenticated SMB to happen. For example, it's not normal if the domain controller connects back through free tiering securities to a machine in the DMZ on SMB. It seems weird. It should not happen that tier 0 connects back to tier 3 with SMB, or directly on the internet. It happens as well. I've left here a few links if you want to access it inside the slides. The slides will be up on the Black Hat website later today. And they all describe how the APA works, the extended protection for authentication. And they are really interesting if you want to check out. Finally, to conclude this talk, I want to remind you of three things on offensive, defensive, and research perspectives. From the offensive side, Microsoft RPCs are a really wide attack surface, which is mostly overlooked, and we should not overtrust it, and that's why we need to disable all the services that we don't use. We can coerce authentications. From a research perspective, we can find RPC calls to automatically. We can automatically find RPC calls to coerce authentications, but it's only a matter of time until a new call is found, because we still have to try them by hand to trigger actually the authentication with a proof of concept, because we need to activate the services. And finally, from a defense perspective, we need to disable all the services, all the unused services on Windows machines, activate APA, and put on network rules and filters to prevent coerced authentications. Thank you for your attention. I hope you enjoyed this talk, and if you have any questions, I think we are running short on time, so you can DM me on Twitter or on Mastodon. Thank you.